Okay, everybody, welcome back. Today we're going over these exercises about average velocity and position time graphs. So I hope that you've done the exercises already. If you haven't, check the link in the description below and go download those exercises. Try them out yourself first and then come back here and then we'll go over them. Okay, so let's continue. The first question says, you get onto a bus to go home. The bus travels in the positive x direction with an average velocity of 36 kilometers per hour for 10 minutes, and then you get off the bus. What is the average velocity of the bus in meters per second? Okay, so first let me try and just draw a little picture of sort of what's going on. So we've got, this is our line, right? So here you get on your bus, right? Over here at the beginning. So you get on this bus and you travel down 36 kilometers per hour for 10 minutes. So you wind up traveling to, let's say, this point B. You start at A, you go to B. Okay, so what is the average velocity? Well, this is simply a unit conversion. Okay, so we're just going to be doing some dimensional analysis. We know that the original average velocity the average velocity in the x direction is equal to 36 kilometers per hour, and we need to change this into meters per second. Okay, so we're going to try and convert this out. Let's get rid of the hours first. Let's convert hours into seconds. So we know that 1 hour is the same as 60 minutes. This will allow us to cancel out the hours, and we know that 1 minute is equal to 60 seconds. And so now this will allow us to cancel out the minutes. So we're left with seconds. Now we need to convert kilometers into meters. And we know that 1 meter, or rather 1,000 meters, is equal to 1 kilometer. And so now we can cancel out our kilometers. And so the only units we have remaining are meters per second, right? So that's how this works. And so we'll do the math here real quick. Let's do the math, get our calculator out. So we have 36 divided by 60 divided by 60 multiplied by 1,000, and that's 10 meters per second. Okay, so there we go. This is our average velocity for the bus in meters per second. Okay, so that's going to answer part A. Part B says, how far do you travel in meters on the bus? So what is this distance here from A to B, right? That's what we're looking for, this change in position, this delta x. Okay, so how do we do this? Well, we know that the definition for average velocity is equal to the change in position over the change in time, or the displacement over the time interval. Okay, so we need to now solve for delta x. So delta x is going to be the average x velocity multiplied by this delta t. There we go. Okay, so this is the equation we're going to have to use. Now, let's plug in some numbers. Our average velocity we just found over here is going to be 10 meters per second, and our delta t is going to be given in our question here. It's 10 minutes. Okay, 10 minutes, but these time units don't match, and so let's convert minutes into seconds. So we know that there's going to be 60 seconds per minute, and so this will allow us to cancel the minutes out, and then this will cancel out the seconds. We'll be left with an answer in meters, which is exactly what we want. And so 10 times 10 times 60, this is going to be equal to 6,000 meters. And there is our answer for part B. Okay, let's continue on to part C here. Unfortunately, the bus stop is not very close to your home. When you get off the bus, you need to walk 200 meters in the negative x direction to get home. It takes you 2 minutes to walk this distance. What is your total average velocity from when you get on the bus to when you get home in meters per second? Okay, so let's just add an extra point C here. Point C is actually your home. while point B is the bus stop, right? And so you actually travel past your home, go to the bus stop, and then walk back 200 meters to get home. And so this is actually what happens for your complete journey from A to C. Okay, so what we need to do is find our total average velocity. That's what we're looking for. And we know that the equation to do this is going to be the change in position over the change in time. There we go. Okay, so but now our points that we're traveling through is from point 1 is point A to point C. Okay, so that's our final point right over there. So let's figure this out. We know that the change in position is going to be equal to x2 minus x1, and this is over t2 minus t1. That's expanding out what this change means. So what is x2? What is this position of C? Well, we see that it's going to be a total of 6,000 meters to get to B. Right, so we go 6,000 meters to get to B, and then we go and walk to towards the negative x direction, and we walk 200 meters. So this is going to be our value for the final position. And our initial position is here at A, which is just the 0, the origin, right? So that's pretty easy. And time to, well, we see it takes 10 minutes to get to point B. So that's 10 minutes to point B. And then it takes an additional 2 minutes, right, to get to point C. So this is going to be our time to the time that we arrive at point C. And then we start at time 0 when we're at point A. Okay, so this is our x2, and this is our t2. And so now we can just do the math here. So this is going to be 5,800 meters over 12 minutes. I should probably write minutes here so we don't get confused. And we want this in meters per second. So we're going to have to convert minutes into seconds. And so we know that there's going to be 1 minute for every 60 seconds. And we can just do the math here. So there's going to be 5,800 divided by 12 divided by 60. Looks like that's going to be about 8 meters per second. And there we have it. That's our answer for the average velocity from point A to point C, from when we get on the bus to when we finally get home. Okay, hope that answers all the questions here for the first exercise. Let's look at exercise number 2. All right, number 2, you live in Nairobi and need to travel to Mombasa to inspect some goods that have just arrived in port, as you do. Normally, this trip takes you 7 hours when you drive an average speed of 70 kilometers per hour. However, today, there is road construction and you drive an average speed of 50 kilometers per hour. How much longer does the trip take today in minutes? Okay, so let's try and identify what's going on and what we need to know. I'm going to draw a little diagram here so that we can see what's happening. So here's the idea. You start here and you end here. Okay, so let's say that we're starting out in Nairobi and we end up in Mombasa. Okay, so our initial normal situation that we'll call situation 1 is that we drive for 7 hours at an average speed of 70 kilometers per hour. Okay, so that's normally what happens, but today it's a little bit different because of road traffic. We are traveling at an average speed of 50 kilometers per hour, but we don't really know yet how long that's going to take. Okay, so we don't have that piece of information, but we do know our average speed. Okay, and what do we need to know? We need to know how much longer does the trip take today in minutes. Okay, so let's call this unknown quantity delta T2 for the second situation, okay? We'll call this one delta T1, and that's 7 hours, right? So what we need to find out to answer this problem is we need to know how much longer it takes. That's delta T2 minus delta T1, right? So this is our goal, okay? So this is our goal is to find the difference between delta T2 and delta T1. Great. Okay, well, what else do we know? Well, we know the equation for the average velocity. So this is probably what we're going to use because that's what we're studying now. So we know that the average velocity in the x direction is equal to change in position over change in time. Okay, that's just what it is. Now, what we don't know in this second situation is we don't know delta t2, right? So we need to find out what this is going to be. So we need to find that delta t2, and we can rearrange this average velocity equation to see that this is equal to delta x over the average velocity in the x direction for the second situation. Okay, so v2 essentially. Okay, good. We know v2, but we don't know delta x. We don't know this distance, this change in position. So how do we find that? Well, delta x we can calculate from our first scenario, and we'll again rearrange the average velocity equation. We'll see that delta x is equal to the average velocity in the x direction for the first situation multiplied by the delta t in the first situation. And we have all of the information there, right? We do have delta t1 and we do have the average velocity. So we'll be able to go through a couple of steps. Once we find the actual displacement, this distance here, then we can plug that in here and we can find how much time has elapsed for the second scenario. And then once we know that, we can subtract the two to find the difference and how much longer it took today to drive to Mombasa. Okay, let's do it. We've identified everything. We've set it all up. Now let's execute. Let's plug in these numbers, right? Okay, so let's do this first part here. We see that delta x is going to be equal to 70 kilometers per hour multiplied by 7 hours, and this is going to be 490 kilometers, and these hours cancel out. Okay, so this is our distance from Nairobi to Mombasa. We've got that. Now let's use the second equation here that we have. We can see that delta t2 is going to be equal to 490 kilometers, that's our displacement, over the average velocity. And we know that this is 50 kilometers per hour. So V2 here is 50 kilometers per hour. We see that these kilometers cancel and that hours gets flipped to the top. And so what is this going to be? It's going to be 490 divided by 50, 9.8 hours. Okay, so this is 9.8 hours. Okay, that's how long it takes. And now that we have this, we have two times, right? We have the second delta t and we have the first delta t. So we just have to subtract them. And so we see that delta t2 minus delta t1 is going to be equal to 9.8 hours minus the normal 7 hours, and so that's 2.8 hours. And we're almost done, except we want it in minutes. We want to know minutes, so it's just going to be a unit conversion now. And we know that for every 60 minutes, there is a 1 hour. And so we just multiply now 2.8 times 60, and we're going to get 168, and the hours cancel, and we're left with minutes. And so this is the difference. This is how much longer it takes today to drive to Mombasa. It takes 168 minutes more than usual. Okay, hope that works out there for question number 2. Let's take a look at question 3 now. Okay, question 3. You have designed a robot that loads, unloads, and transports pallets of goods down a railroad. Today, you're testing it out. The robot starts out at point A with a load of rice. It travels down the railroad in the positive x direction at a constant velocity and arrives 150 meters away at point B in 100 seconds. It then stops at point B for 200 seconds as it unloads the rice. The robot then continues traveling in the positive x direction for another 50 meters in 100 seconds and arrives at point C. It then stops here for 300 seconds to pick up a load of kitty litter And finally, it travels back to point A in 150 seconds. Draw an XT graph of the robot's journey. Okay, so we've got a very verbose question here. A lot of things happening. This robot is picking up and dropping off things as it travels down this railroad. And we need to draw an XT graph, a position time graph for it. Okay, let's try and set up our axes here. So this is going to be our position graph. Position axis is going to be over here, right, meters, and this is going to be our time axis here in seconds. Now what we want to do is we want to choose some good scale that we're going to work with here, right? So here's 0 and 0. So far as time goes, if we add up all the times, I believe the total amount of times added together is going to be what is 100 plus 200 is 300. 300 plus another is 4. 4 plus another 300 is going to be 700. Plus another 150 is 850. So we're going to have about 850 seconds total for this entire journey. So let's just try and put together a set of axes here that makes sense, a scale that makes sense. So what I want to do is I'll say that this is 100 seconds. This is 200. This is 300. This is 400. 500, 600, 700, 800, 900, and 1,000 seconds. Okay, so this is my axis for the time. And on the vertical axis, it's a little bit harder. You'll have to go through it to try and figure out a good scale here, but I'm just going to use something that I think will work. So I'll say this is 10, 20, 30, 40, 50. 50 meters. Okay, so I've got a scale here that goes, every line is 10 meters, and it goes all the way up to 200 meters. So let's sort of draw a little diagram showing what's happening. So if we imagine there's a vertical here track, this is going to represent the railroad track. And so on this railroad track, we're going to have our robot that travels back and forth along this railroad track, and it's got some mechanical arms so that it can pick up, load these pallets of goods. We're going to see that point A is where we start out, right? So this is here at position 0 meters. We're going to call this point A, okay? And we see that it's going to travel 150 meters away to point B. So point B is going to be here, right? Here's point B, 150 meters. And then after that, it's going to travel an extra 50 meters to get to point C. And so point C is here at 200 meters. Okay, so here are the 3 points laid out on the railroad track. And we've got this parallel to our vertical axis here on the XT graph so that we can see where those locations are on the graph. Great. Okay, so let's draw this graph first. So we're going to start out at point A. Right, and we're going to travel to point B, which is here, 150 meters, and it takes us 100 seconds to get there. Okay, so 100 seconds is going to be here, good, and then it stops here for 200 seconds as it unloads the rice. So this is 100, 200, okay, so it stays until here, and then it's going to continue traveling to point C, and that's going to be point C. It's going to take 100 seconds to get to point C. So that's going to be 100 seconds it takes to get there. And then it stops here for 300 seconds. This is 300 seconds, and that's when it leaves. And it finally travels back to point A in 150 seconds. So it's going to travel here, point A, in 150 seconds is when it gets back. So these are sort of the important points, and we just need to connect them now with our ruler. We can draw some straight lines, sort of like this. Okay, so we've got this line here, and then we've got this line here. We've also got this line right over here. Let's bring the ruler back. Like this. and then it comes back down to point A, something like this. Beautiful. Okay, so here is our position time graph for the robot traveling down the railway. Hope this makes sense. Let's look at point B. What is the slope of the line as the robot moves from point A to point B? And what is the average velocity of the robot as it moves from point A to point B? Okay, so what it's asking is, what is the slope of this line right here, right? As it's moving from point A to point B, what is that going to be? All right, well, we can calculate that. So we know that the slope of a line is going to be equal to the change in the vertical distance, which is going to be change in x, over the change in the horizontal distance, which is change in time. Okay, so change in our x position, we can see that it goes to 150 meters minus 0, which is where we started. And then our time, it takes 100 seconds to get there. And we started at 0, so you could add a minus 0 if you want. Or you can just do 150 over 100 here. And so this is going to equal a 1.5 meters per second. Okay, so this here is the slope of the line. And you can see that this equation of change in position over change in time, this is also the equation for the average velocity. And so this is also equal to the average velocity in the x direction for the robot during this interval here. So they're the same. Okay, that's the point. The slope of the line and the average velocity are the same. Great. Okay. Part C, draw another line on the graph and use it to calculate the average velocity of the robot when it first arrives at point B to when it returns to point A. Okay, so let's do this. Where does it first arrive at point B? Well, that's going to be it's going to be here, and then when it arrives at point A, let's use a different color. So it's going to be this line right here. That's the line we're talking about. Okay, this is for part C, right? This is when it first arrives at point B to when it finally returns back at point A there. And now we want to calculate the average velocity, which is going to be equal to the slope, right? We can see these are equal, and so this is going to be equal to the change in the vertical axis over the change in the horizontal axis. So x2 minus x1 over t2 minus t1. Okay, so what is our x2? x2 here is going to be 0 meters, right? 0 meters. And x1 is here at 150 meters. 150 meters. Time 2 is 850 seconds. And time 1 is 100 seconds. So if we do this, this is equal to minus 150 meters over 750 seconds. So now let's do the math here. So we've got 150 meters, and that's negative, divided by 750 seconds. That's negative 0.2 meters per second. Okay, so we've got here is negative 0.2 meters per second. I'll just sort of squeeze that in right here. This is the average velocity between this point and this point on the graph. Okay, that is C. And now finally, we come to question D, and it asks us, what is the average velocity of the robot for the entire test run? And this is a trick question because the average velocity here is going to be 0 meters per second. Okay, I hope you see that. And the reason why is because, well, the displacement is 0, right? It starts here at position A at 0 meters and it returns, it ends back at 0 meters. So the total displacement of the entire test run is 0 meters, right? We can do this math if you want to. Right, the average velocity here is going to be delta x over delta t, and this is going to be x2 minus x1 over t2 minus t1. And for the time is not 0, right? This is 850 seconds minus 0 seconds. But if we look at the displacement, x2 is here, which is at 0 meters, right? So 0 meters, and x1 is here, which is at 0 meters. And so definitely we have 0 over 850, which is equal to 0, and so it's 0. Okay, there we go. These are the answers for the 3 exercise questions for average velocity and interpreting a position time graph. I hope this makes sense for you. If you had any mistakes going through it, hopefully this shows how to sort of do it correctly. If you have any questions or you still don't understand something here, leave me a comment below and I'll try and answer you. If this helped out, give me a like or give me a sub. That really helps me out a lot. And in our next chapter, we will be going over how to look at some velocity that's not average. We'll be talking about instantaneous velocity. So be further developing our concept of velocity, and we will continue to use position time graphs because they become more interesting as we delve further into kinematics and one-dimensional motion. Hope to see you there. Thanks a lot. Bye-bye.